So welcome to the fourth DP Roy Memorial Lecture Series. As you know, we started this lecture series about 5 years ago in the memory of our dear colleague, Professor DP Roy, who worked in high energy physics. This is, of course, possible because of the generous endowment by Dr. Monica Roy, who is also here. We have had three eminent scientists giving talks in this series before. The first was given by Professor Christoph Groja, the second by Kate Scholberg, and the third by Rohini Godbole. The third talk, unfortunately, had to be only online because we were in the pandemic then, but we are very happy to revive this series with in-person talks. And we are very happy to have Professor Csaba Csaki from Cornell University to give us this talk. Before we go to the talk itself, let me invite today's speaker, Professor Csaba Csaki, TIFR Director, Professor Jairam Chengalur, and Dr. Monica Roy on the stage. So let me request the TIFR Director, Professor Jairam Chengalur, to say a few words of welcome.
I really don't have that much to add to what Amol said. It's a great pleasure to extend to you my personal welcome and also, of course, welcome on behalf of TIFR for those of you from outside to this lecture in memory of Professor DP Roy. And as Amol said, he has had many decades of association with TIFR and his contributions, which we'll hear about, I think, in a little bit more detail shortly, particularly in the areas of supersymmetry, especially the search for the charged Higgs. And he also played a very important role in zooming in on the parameter space for solar neutrino oscillations. After he retired, Professor Roy was also very active at HBCSC, and he was participated in the NIUS, which many of you would be familiar with, the National Initiative for Undergraduate Sciences. And he was very active till the very end. And so it's very fitting that we have this lecture series in his honor, and we are very grateful to Dr. Monica Roy for setting up this endowment, which makes it possible. As Amol said, we've had a series of very excellent lectures over the years. And this year also, we have a very eminent speaker, a distinguished speaker from Cornell University, Professor Csaba Csaki. And so along with the rest of you, I'm really looking forward to this talk.
Thank you, Professor Chengalur. Professor Roy, of course, was in TIFR for many decades, and he also has a lot of collaborators here. I would like to invite one of his collaborators and a member of the DP Roy Memorial Committee, Professor Manoranjan Guchait, to say a few words about his science. Manoranjan.
Thank you, Amol. And good afternoon, everybody. So it's really indeed honor for me to speak about late Professor Durga Prasad Roy on behalf of DP Roy Memorial Lecture Series Committee. It is also very nostalgic for me. I think several of us who are present in the audience or maybe in Zoom, they know who is DP and what is his contribution. But nevertheless, for younger students and the younger colleagues, I just want to remember what what DP has done in particle physics. Professor DP was associated with the Department of Theoretical Physics in TFR for more than 30 years. He passed away on March 17 in 2017 after a very brief illness. His sudden demise left his family and many of his friends and collaborators in a state of utter shock. And one morning, suddenly we heard this news, suddenly. He was then 76 years old and survived by his wife, Dr. Monica Roy, and daughter, Ms. Kulyani Roy, and she is supposed to join us. She is on the way. I think she will reach here very soon. And that time he was having two very nice grandchildren. Professor DP Roy, popularly known as DP, and we used to call him Durgada in Bengali style, one of the best known phenomenologists internationally well known. Here the phenomenologist means who really works in the interface between theory and experiment. Okay, he has carried out research over a wide range of topics in particle physics. In the very beginning of his career, he worked in the very low energy QCD and also the hadron spectroscopy. With the advent of the new generation of experiment, in particular the colliders, such as Lip colliders, Staberton, and then LAC, he then shifted his focus towards more the collider-based studies. Okay, in particular, the top quark physics, he is one of the experts in the top quark physics, Higgs physics, looking for the beyond standard model physics, in particular, supersymmetry in colliders. DP was also equally interested in astroparticle physics, where he used to work in the area of neutrino physics and dark matter physics and the interface with the colliders. Okay, for more than 3 decades, he has published more than 200 papers, including some very comprehensive review articles. Some of his works, which are basically more collider based and also neutrino physics, are referred by various experimental collaboration. This is something to achievement. When the experimental collaborators acknowledge or cites any paper of any theoretician, that is some sort of acknowledgement that indicates what kind of contribution or what kind of content of that paper has. In the 90s, DP was the leading person in our country who first introduced and taught us the collider phenomenology. Afterwards, many students started working on the collider physics. I am one of them. I do not have any hesitation to acknowledge his contribution in bringing the collider physics culture in our country at that time. Being a theoretical physicist, he also had a great interest in experimental high energy physics as well, I think, which made him a great and expert in collider physics. DP was very affectionate with younger people, a quality which attracted several graduate students and postdoctoral fellows to collaborate with him on very easy terms. He was equally passionate about undergraduate teaching and very keen to spread science among younger generation, in particular girl students. Maybe with this inspiration, with that kind of inspiration, and also his family understood that. So his wife, after his sad demise, his wife, Dr. Monica Roy, and her daughter, family have created an endowment for conducting this lecture series for young students, which we are conducting today. This is a 4th lecture series we are happening, or already I mentioned it. DP was also very fond of traveling and adventure. He also had a keen interest to read and learn history, either it is in mythological or it is science. Okay. Last but not the least, he was a great lover of Indian classical music and dance. Okay, maybe from that passion, DP himself instituted the Kabiri Memorial Music Show in our campus, which is organized in every year. I think it will be more than 10 years. It is running on. In this music show, all of us, including our family members, we do participate either as an artist or in audience. Although I have several things to share with you, but I don't want to take much time, and I don't want to continue that. we listen about the topics, what DP was working and DP contributed in that area of physics. Let us listen from one of the renowned speaker. So I stop here. Thank you very much for your listening.
I would like to request Dr. Monica Roy to say a few words.
Hello, good evening to everybody. My name is Monica Roy. Professor D.P. Roy was my husband. Actually, when the D.P. Roy Memorial Committee invited me, I was very, very happy. This time, I got two invitations, one from D.P. Roy Memorial Committee and one from Theoretical Physics Group. So I am really fortunate to be invited here and speak a few words for this on this occasion. Many things are coming into my mind. It's very, very nostalgic and it is quite emotional also. We look for every chance to come to TIFR because we have spent 30 years in TIFR colony and we are benefited by our state tremendously. And DP, of course, was associated with TIFR more than 40 years. So every time, every occasion I get to come to TIFR, I take it because it is like coming home to me. So many memories, good memories are associated with TIFR and TIFR colony. And it is a good opportunity for me to see the people, meet our friends, new and old. And through this memorial lecture, not only the people, but also the administrative head and the dignitaries and eminent professors I meet, which are very valuable in my life. Otherwise, it is difficult to meet anybody. Let me start by thanking our director, Professor Jairam Sengalur, to grace this occasion and giving a few words or speak a few words about my husband, Professor D.P. Roy. I am grateful to Professor Csaba Csaki. I'm correct, no? Csaba Csaki for accepting the invitation and agreeing to deliver today's public lectures and other lectures. We are eagerly waiting for your lectures. The lecture has a very interesting title, Particle Physics as Crossroads. I am sure everybody will enjoy the lecture and that will enlighten the current development of particle physics. Actually, coincidentally, I want to say something. Before my husband's death, that was in March 17, he went to Hyderabad to give a seminar. I think it was some school, I think. And there he taught student standard model. He was very appreciated. Everybody appreciated his lecture. I know it from the condolences messages. And after that, he became sick and it was all on a sudden he passed away. So, and I am really honored to get this invitation from Professor Gautam Mandal. This is the head of Theoretical Physics Department and Professor Amol Dige, head of the DP Memorial Committee. And my sincere thanks to both of them, Theoretical Physics Group and DP Roy Lecture Committee, to arrange this beautiful event. I am very much touched by the love and respect you have shown to my late husband, Professor D.P. Roy. And I think the same spirit, enthusiasm continues and present, and the present and future generations of students and research workers benefit by sharing their knowledge with experts in the field, and public in general will also be able to know the progress of the science through this lecture series. I am really, really happy. And I think this is the best way to pay tribute to my late husband, Professor D.P. Roy. According to Hindi mythology, people die, but soul lives. So death, they say, is the union between soul and Almighty. So wherever DP is, he will be definitely happy to listen to this lecture. So that's all. DP was very passionate about teaching. Research work, TIFR people will be knowing better and they will tell. And DP was very passionate about teaching, all types of teaching, not only science teaching, in the even in the school teaching, and also teaching my grandson, who is only 3-year-old. And he generally, he feel comfortable with the younger generation. Not only teaching, he used to do all sort of extracurricular activity. I think many people have seen during the web meeting that after the lecture, he will go to seashore. If it is, I think he enjoyed very much in the meeting at Tosali in Konark. So he used to go to seashore with the students and doing all sorts of extracurricular activity. And he, in TIFR, when he joined, he worked with Professor Udgawakar. And he taught many things from Professor Udgawakar. I think two most remarkable things which helped him was the writing scientific papers. He learned from Professor Udgawakar. And second thing, which influenced his life, is to give to the future generation the experience and knowledge. It is passed on to the future generation with a very strict censorship about co-authorship. Professor Udgawakar himself, he used to teach DP, taught DP, but he never put his name in his paper. He used to say that it is your work, your name should be there. DP also followed that principle. If he has worked for the paper, he used to put his name, otherwise not. So this is all. I think this lecture will continue. And actually giving donation, the endorsement is not a big thing. It was my husband's wish that part of his savings will go for good work. And I am only a custodian of his money, and what I have thought it will be best, what I have done, with full cooperations from his students. And students he used to fondly call student, and students he used to call grand student. This is why he used to feel that this is in one family. So it is mainly the interest of the people of theoretical physics group and DP Memorial Committee that this lecture is going on. And really appreciate the trouble they have taken. And they have taken the trouble. And when I started this, proposed for this lecture series, I was a bit apprehensive because everybody in TIFR is so busy, whether they will give time. And there is a lot of bureaucratic and administrative restriction, but they have overcome everything. And I am very happy that it came through. and let it pursue. That's all. Thank you very much.
Thank you, Monica Di. We all remember DP as a colleague and as a person very, very fondly. Let me now request our director to formally welcome Professor Csaba Csaki with a bouquet and a gift. Let me now invite Professor Tuhin Roy to introduce the speaker.
Mike? Oh, yeah. Okay, so it's truly an honor to be given a chance to introduce Csaba Csaki. So first time I came through him was actually not in person. In first summer of my graduate school, my advisor gave me a collection of papers, told me go learn supersymmetric theories, and he disappeared in the mountains of Aspen. Okay. And there, those remarkable papers, that was one summer I had to struggle, and found this incredible set of exact results, and many of them were from Csaba and his collaborators. Later, I met him in person in Cornell, and while I was talking to him, I realized that he published all these papers while he was still a graduate student. Okay, he was already a star when he was finishing his PhD in MIT, and then he moved to UC Berkeley as a Miller Fellow for a couple of years. Then he was the Oppenheimer Fellow in Los Alamos National Lab. 2 years later, he moved to Cornell University, and he's there till now. Okay, and in these years, he has worked on anything a typical particle theorist works on, from theories of supersymmetry, theories with extra dimension, composite Higgs, collective supersymmetry breaking, little Higgs, twin Higgs, and all possible combinations you just name. In formal, he works a lot on formal theories, and recently Csaba and some of his collaborators have devised a wonderful technique via which they are bringing those exact results which are valid in the domains of supersymmetric theory to non-supersymmetric theories, okay, in real world. To say we'll hear more about it on Thursday, and so please come and listen to him on that. So it would be a technical lecture, but it's worth listening to him. So apart from physics, he is extremely knowledgeable in world politics. So if you want his opinion, go ahead and you'd have a nice chat with him. But I'll not take much more time. Let me just give the podium to Professor Csaki to talk about particle physics at the crossroads.
Thank you to him. Yeah, I will request the director and Professor Roy to you can sit in front, and maybe I should just mention in passing that Csaba and I went to the same Tasi summer school, and he, I think, was a senior guy, already started writing papers, and he was one of the guys who made me actually start writing my first paper. So we go back along. Yes, Csaba, please.
Thank you very much. Thanks, Amor, for the nice introduction, and to him. Yes, so in fact, yeah, we do go back to 1995, and I'm really glad to be back here and be able to give the DP Roy Memorial Lectures. It's my second time in Mumbai. First time I was here at the conference that Monorajan organized 5 years ago. So I'm really glad to be here. So the plan for today is to give a non-technical lecture and give you basically a status of where does particle physics stand today, and what are the issues that are keeping us up at night, and what are the big questions, and what are the directions that we are trying to use in order to solve these. Okay. Good. All right, very good. So let's first start with the very basics. What is particle physics exploring? It's exploring the 4 basic forces of nature. Everybody knows what they are, the electromagnetic interactions, so that really everybody knows. If you don't know about the weak interactions, well, you probably do know because that's the origin of radioactivity. The strong interactions are the force that keeps that binds nuclei together, and also the origin of energy production in the sun. And of course, everybody knows about the gravitational interactions, which are responsible for the motion of planets, rockets, etc. It turns out that the gravitational interactions, even though that's the one that we are most familiar with, actually on very small distances are very weak. And even though it sounds counterintuitive, you can understand that a small magnet can balance the effect of the entire Earth pulling an air back. So it's actually a much weaker interaction than the others. So it's really usually not very relevant in accelerators. So for most of the time when we are talking about accelerator-based particle physics, we are not very much dealing with the gravity. We are dealing with these other three interactions. So how do we model particle physics interactions? I have a really nice cartoon here, yes, that is trying to explain what the modern way of describing the interactions of the different particles are. So imagine that you have two skaters skating past each other, and they would start out parallel. And one skater, for some weird reason, happens to carry a big bowling ball and passes the bowling ball to the other skater. Yes. What happens is that when the skater passes the bowling ball, both of their paths will deviate from the original parallel interaction, and it looks like there was some sort of an interaction between the two skaters. Yes. And that's actually mediated by the exchange of this bowling ball. Okay, so this is actually, again, a very nice cartoon illustrating the way we are thinking about the interactions, the various interactions that I was telling you about before. So, for example, if you look at the electromagnetic interactions, that interaction would actually be mediated by the exchange of a photon, which is the quantum, the mediator of the electromagnetic interactions. Okay, and you see that these little stick diagrams, these are called the Feynman diagrams, and those are, again, sort of in some sense, the physics description of this little cartoon that I was trying to use here. Okay, so this is, again, essentially this is the theory of quantum electrodynamics, that you have some particles that carry electric charge, and those are going to be interacting with each other by the exchange of a photon, and the exchange of the photon will be proportional to the electric charge of these various particles. Okay, so this is what is now called quantum electrodynamics, the quantized version of Maxwell's theory, the quantized version of E&M that everybody in grad school is being forced to go through. And one of the basic principles behind E&M is the so-called gauge invariance. This is, so often it's also called the U1 gauge theory. And that's what is actually keeping the photon a massless particle. Okay, so Feynman was the one, even though quantum electrodynamics was developed in the 30s, so it wasn't developed by Feynman himself, but the relativistic modern version, the modern notion of using these Feynman diagrams and getting a fully relativistic theory, that goes back basically to Feynman, and he got the Nobel Prize for this in the 1950s. And I put up this paper just to remind you that even though almost everybody associates Feynman with Caltech, his most important paper related to quantum electrodynamics was actually written in those few years when he was at Cornell, right after World War II, and he came back from Los Alamos. Okay, very good. So that's how we think about electrodynamics. Now, how do we think about the weak interaction? Yes, so I told you, again, that's the one that is responsible for radioactivity. And for a long time, on first sight, it looks a very different kind of interaction. We call it weak because we think it's weak compared to the electromagnetic interactions. Also, the electromagnetic interaction is very different in the sense that it has a very finite interaction range, while electromagnetism, has an infinite range. The Coulomb law is a 1/r potential that doesn't die off suddenly at a particular range. So for a long time in the early 20th century, it looked like they are really two very different interactions. However, by the 1950s and then gradually by the 1970s, it became clear that actually the weak interactions are not that different fundamentally from the electrodynamics, as I mentioned before. In fact, it will have also its own mediating particle. And physicists, of course, you know, they call this the W particle because it's the mediator for the weak interactions. Okay, and the main difference between the electromagnetic and the weak interactions is the property of the W particle. Namely, the W particle is actually massive, unlike the photon. And that is what is giving rise to the finite range of the weak interactions. And the other big difference is that this force carrier of the weak interactions is actually itself charged. It carries electric charge, unlike the photon, which is chargeless. But in other ways, it's actually very similar. So the probability of emitting a W particle is actually intrinsically almost the same as emitting a photon. And the interactions also occurred the same way. The main difference is, again, that because the W particle is massive, it itself is an unstable particle and lives only for a very short time, and it will itself decay. And this is what is giving rise to the short finite range of the weak interactions, which make it appear to us as being much weaker than the electromagnetic interactions. And there's one other twist here, that it turns out that there is a sister for these W particles, which is called the Z boson, which is another force carrier for the weak interactions. And it's also massive. And the main difference is that the Z boson is actually electrically uncharged. It's an electrically neutral particle. So it's like a very heavy version of the photon. Okay. And so the W particle was essentially already assumed by Fermi or in his time, but you know, the presence of the second force carrier, the Z boson, so that was essentially postulated by these people who came up with the theory of the weak interactions. In fact, it turns out that the only way to formulate the proper theory of the weak interactions is to unify it with electromagnetism. So in fact, the three of them, you know, Glashow, Salam, and Weinberg, they worked out the theory of the unified electroweak interactions in the very late 1960s. And then in 1982, finally, you know, the Z boson was actually verified inside the collider experiments, and they also got the Nobel Prize for it. Now there is a third type of interaction that I mentioned, which is the strong interaction. And that one really, again, looked super different from the electromagnetic and the weak interactions. And again, you know, the first way we learned about them is essentially that, you know, you have to have some force that is keeping protons that are all electrically charged together inside the nucleus. So it's got to be something that overwhelms the electromagnetic interactions. That's why it's called the strong interaction. And so this had its own very long story of development, starting from the 1950s, when a lot of new particles that are strongly interacting were discovered, until the 60s, when Gell-Mann was able to find what, you know, really the fundamental description of the strong interactions is. And I will tell you more about this, and also you know, the story of quarks. But the upshot is that deep down, the final theory of strong interactions that we know now is the right theory is actually not that different from these other two, the weak and the electromagnetic interactions, in the sense that it also has a force carrier. We call this the gluon. It's also massless. So in that sense, it's more similar to the photon, to the force carrier of the electromagnetic interactions. The main difference is that the emission of a gluon has a very large probability. So when you try to describe the strong interactions among the quarks, it's actually not a very good picture to just think of it as the exchange of a single gluon, because the probability of emitting one is very large. And then the gluon, there can be 2 gluons emitted and 3 gluons emitted. And in fact, the gluon itself can split into 2 other gluons, which is different from the photon. And basically, there will be this big mass, which together all make up the strong interactions. But the underlying theory is, in fact, very, very similar. And again, of course, the reason why it's called the gluon is because this is the particle that glues the quarks together to form bound states like the protons. Okay, and again, I mentioned already briefly that the big discovery that led eventually to the correct description of the strong interactions was the fact that the protons and the other sort of strongly interacting particles that were discovered in the 1950s are actually not the fundamental particles that feel the strong interactions, but those are actually the quarks. And that was due to Gell-Mann and Zweig in the 1960s, who were able to put together, to classify the various strongly interacting particles. And from there, it became clear that there's going to be some more fundamental objects whose bound states you can think of as the observed strongly interacting particles. And that, classification then made sense of all the many hundreds of particles that were discovered in the 50s in terms of just a few basic elementary particles. Okay. Now, one thing that was a twist about it is that, okay, it's very nice to postulate these quarks, but where are they? Why have we never seen them as free particles? And the postulate by Gell-Mann was that actually, they are always confined, that the strong interaction is so strong that you will never see them as elementary particles. And that was kind of, a puzzle for a long time until people started understanding this other story of asymptotic freedom of the strong interactions. And that's another work that got the Nobel Prize for Gross, Politzer, and Wilczek in 2000 something something like that. And that's a very counterintuitive result, because what it is telling you is that actually the strong interactions, as you go to higher and higher energies, actually become weaker. Okay, so if you go to really, really high energies, the strong interaction, the strength actually goes to zero. That's what this weird name asymptotic freedom actually stands for. That asymptotically, for really, really large energies, the quarks, even though we never see them as free particles in nature, they act as free particles. Okay. And the really counterintuitive part is not the fact that the strength of these interactions is changing. That's something that we are used to from condensed matter physics and other parts of physics. Just the fact that charges get screened, and when you look at long distances, you don't see all the charges. You see just a smaller amount of the charge because it's surrounded by some sort of a cloud of other particles. The weird part about asymptotic freedom is that it's opposite to the effect of the usual screening that we are used to in other parts of physics. Essentially, there's some sort of an anti-screening effect. That's how you go to longer distances. The interaction actually becomes stronger rather than weaker, as you would naively expect in ordinary screening mechanisms. So that's the story of asymptotic freedom. And again, this is just telling you that this is what is called alpha S, is the strength of the strong interactions, and it's becoming smaller and smaller as you go to larger distance scales. Okay, so these are the basic ingredients of what we call the standard model of particle physics. So this is the famous slide from the particle data group. It's telling you that there are these force carriers. Yes, these are the ones that we have been discussing before: the photon, the gluon, and the W and the Z. And then there are the matter particles. Those are the particles that feel these forces. Those are the ones that are actually exchanging these force-carrying particles. They form bound states. So these are the observed particles. And essentially, this is what we call the standard model of particle physics. Now, if you want a more formal description, I won't be needing this, but just as a reference, you can formulate this as what is called the gauge theory, which is, again, a generalization of Maxwell's electromagnetic theory. So you have sort of the generalization of the field strengths tensor, except, those are now going to be describing the objects that are made out of the force-mediating particles. So there will be sort of an analog of a field strength for the strong interactions, which you usually call color, field strength for the weak interactions, etc. And then these are, again, the matter fields, the ones that are exchanging those force-carrying particles. Now, there's one other object here that I haven't talked about, and of course, the reason is because this is going to be a big part of this talk. This is the so-called Higgs boson, and this is an object that, right now doesn't fit into, all the other parts, the matter fields or the force-carrying fields. However, it turns out that without this, as I will explain, the theory is actually not complete and doesn't, it doesn't give you the observations that we want. Now, the standard model before this, the LHC, which will be again also, of course, a big part of this talk, before it was turned on, almost every aspect of the standard model has been verified in great detail by several experiments, mostly the so-called LAP experiment, Large Electron Proton Electron Positron Collider at CERN, LAP and LAP2 in the 1990s, and not just verified somewhat, but you can see the error bars are just staggering. It's essentially 0.1% level measurements for upward of 20 quantities, that something that you could calculate in the standard model and then have some very precise measurement for it at LAP, and then there was another experiment at SLAC, and then of course at the Tevatron. Okay, now the one thing that wasn't verified prior to the LHC about the standard model is the so-called Higgs sector. And what we physicists say is that actually the electroweak symmetry, the symmetry that is responsible for the electroweak interactions, is actually spontaneously broken by what we call the Higgs boson. Okay, so how do we know that? Well, if the symmetry, the so-called electroweak symmetry, was actually intact and an unbroken symmetry, it would actually make all the gauge boson masses to be vanishing. So to begin with, without this electroweak symmetry breaking, the W and the Z boson would actually be almost identical to the photon. It would be massless. It would give rise to long-range interactions. There would be some subtleties there, but essentially would be very similar to the electromagnetic interactions. And similarly, all the fermions all the elementary fermions that we know in nature, the electrons, the quarks, and the heavier versions of them, they would also have to be massless, exactly massless. Okay. So that's, of course, in stark contradiction with what we are observing, yes. So because of that, there's got to be a way to reconcile the fact that, this theory of the W and the Z is such a fantastic description of nature, but you need to make them massive. Yes, this is where the story of electroweak symmetry breaking and the Higgs sector comes in. So the assumption will be that in addition to the fields to the particles and their corresponding fields that I have been discussing, there's one more field, there's one more sector which is called the Higgs sector, and that's the one that is giving rise to electroweak symmetry breaking such that it's in the vacuum, the Higgs boson itself is actually choosing the preferred direction for the electroweak interactions. And that vacuum expectation value, that's what we call it, this vacuum expectation value for the Higgs field is what is actually allowing you to generate a mass for the W and the Z boson and for all the quarks. So the way to think of this, the analogy is that the entire space is actually around us is actually filled with a condensate of this Higgs field. And as the particles are moving in this background of the condensate, you actually feel the presence of this condensate. And you can think of it as, this drags the particles that are moving in it, it slows down their motion, and effectively it will appear as if they become massive particles. Okay? So it's somewhat like a theory of ether, yes? Basically people thought that there is sort of something like a fluid that is permeating all of space. This is ether. This is, the medium in which the electromagnetic waves are propagating. And then, of course, Einstein realized, after the Michelson experiments that, that doesn't exist and it doesn't make any sense as there is no ether. So the thing that you have to ask is, how can I reconcile the fact that I'm telling you that there's this, all of space is permeated by this fluid, yes, and it still doesn't contradict relativity, yes, how can I reconcile these two facts, because Einstein is telling you there is no ether. I or Higgs or whoever in the 60s was telling you that there is something like an ether. Well, it turns out that there is one way out that can give you both of these worlds. If this fluid, this Higgs condensate, is actually something that is not breaking relativity, so it actually looks from every reference frame the same. So it has to be a different kind of particle than what we have already observed in nature. This is why the Higgs boson has to be a scalar particle. Okay, if it was a fermion and it condensed, then it would break relativity, it would be excluded by the Michelson experiment, and we couldn't do anything about it. But if it's a scalar, yes, the condensate of a scalar looks the same in every reference frame. Okay, so that's why the Higgs boson has got to be very different in nature from all the other particles that we have observed so far. Okay, so that's the story. Okay, so that's the way that we are actually imagining the Higgs mechanism happening. So there's this scalar fluid, so it's a relativistic ether. Okay, and depending on how much the various particles feel the presence of this fluid, of this Higgs fluid, they will be dragged down by different amounts. So the photon doesn't feel it at all, so it will still propagate with the speed of light. The electron has every now and then some interaction, so it will slow down a little bit. The top quark, the heaviest particle, it slows down a lot. Okay, so what people usually say is that the analogy is that this is like a viscous damping force that is slowing down the motion of the particle, like a ping pong ball that is being dragged in honey. Now that sounds nice, but it's not quite the right analogy, because if you know a little bit about damping forces, you realize that that's actually not what looks like a mass. Yes, so if you did a basic physics course, then you learn about the various damping forces, and you learn about a viscous damping force or a turbulent damping force. And those are either proportional to the relative velocity or the relative square of the velocity of the object that is moving in that particular background. Yes. And that's not quite what the Higgs is. So the right analogy would be to sort of postulate a damping force, which is not proportional to the velocity of the particle that is moving in that particular medium, but it's actually proportional to the acceleration of the particle. Yes? So if there was such a thing, I call this the Higgs damping force. Yes. Then, okay, so then the force acting on the particle would be proportional to the acceleration of the particle. So now if I assume that I have a fundamentally massless particle that is sort of interacting with this Higgs damping force, yes, then if I go ahead and write down Newton's law of motion, yes, which is that F equals mass times acceleration, yes, but the mass of the particle is zero, so the total force has to add up to zero, yes, but one of the forces is this damping force that is proportional to the acceleration of the particle. So you see the total forces outside the damping plus the damping force is zero. Yes, so now if I rearrange this equation, it will give me sort of an effective version of Newton's equation, where it tells me that all the forces now sum up to something that is proportional to the acceleration of the particle. Yes, so this B, this damping coefficient would effectively appear as if it was a mass for the particle. Yes, so I started out with a massless particle, but due to the interaction with this weird acceleration damping force, yes, it looks like due to the interaction with that fluid, the particle gained a mass. So this is sort of the correct analogy for the Higgs mechanism, and this is in fact how we are actually thinking about the Higgs mechanism in particle physics. Okay, so we know there should be a Higgs field, yes. This is the one that I described that is filling all of space. Now, if there is a Higgs field, the Higgs field itself should have its own excitations. There should be a particle corresponding to the fact that, okay, we are sitting at one of these vacua, yes, which is breaking the electroweak symmetry, but the field can sort of oscillate a little bit around this, and that should be a physical particle. Okay, so that's what is called the Higgs boson. So the Higgs field is the thing that is permeating all of space, and then the fluctuation of the Higgs field is giving rise to the Higgs boson. So that's what people used to call the holy grail at some point of particle physics, which is sort of, if we discover that, that would be a proof that this is in fact the way, the electroweak symmetry is actually broken in nature. Okay, very good. So now comes then the story of the discovery of the Higgs boson. So this, of course, so the LHC was not the first experiment that was searching for the Higgs boson. The predecessor experiments, the ones that I mentioned, the Tevatron at Fermilab and LAP, and previous smaller experiments, lower energy experiments, they were all searching for the Higgs boson, but all they could find is that it's not there in the energy range where they are actually that they were actually able to reach in their accelerator. So that's why one of the main reasons why the LHC was built at CERN in Geneva in Europe. So this is a 17-mile circumference accelerator, and in fact the tunnel is the same tunnel that was built already for LAP, the one that I mentioned to you, measured all those many precise experiments for the electroweak precision observables. Okay, so this is, again, there's a nice cartoon here just to give you some scales. Over 6,000 scientists, 500 universities all over the world. Here's a little cartoon of what the LHC actually does. So there are two main experiments. They are called multi-purpose experiments, ATLAS and CMS. So they're essentially, they're looking for all kinds of particle physics processes. And then there are two more specialized experiments. One of them is looking for the properties of the B meson and the B quark. That's called LHCb. And then the other one is built mainly for heavy ion collisions. It's called the ALICE experiment. Okay, so here, a few decades ago when I was a little younger, and the LHC was still under construction, you can see just for scale, how these experiments look like. I put up a few facts here from the LHC website, just to see how mind-blowing this whole thing is. Almost 10,000 magnets, biggest refrigerator in the world. The protons are accelerated to 6.5 TeV. First, it turned out, we'll get to that story too. It was 3.5, one of the best vacuum in the world, 10 to the minus 13 atmospheres. The number of collisions is close to 1 billion per second, and the accuracy of timing is really all of these results are mind-blowing. This is the biggest supercomputer in the world. The data is filling up, 100,000 DVDs per year now. Of course, people don't count DVDs anymore, and that's just the data that they are actually gathering. Many of the data, there's so much data coming in that they really physically are not able to record all of them. So they have to, in real time, decide which one is an interesting collision and which one is a sort of a boring collision, and they only try to record the ones that are interesting. And if this is not enough, in a few years they are already working hard on the luminosity upgrade of the LHC. There will be even more collisions, and in 1 year they will collect more data than the total of the previous runs until then. Okay, so the LHC started in 2008. And everybody was super happy. This was the first image of debris from CMS. But then actually something catastrophic happened very soon, just within a few weeks. And everybody was really worried, what will be the future of the LHC. There was what is called a magnetic quench. Some of the connections between the magnets was not properly prepared. And essentially, part of the LHC, really blew up. And you see, part of the LHC, there was no signal there. The magnets essentially had to be rebuilt, for part of it. So that was very worrisome, and it was quite amazing that they took only about a year after this really bad. They called it the event, to restart the LHC, and by the spring of 2010, they were able to actually have collisions happening inside the detectors. Okay, so this again, it was at 7 TeV. So that was the reason why they lowered the energy, because they wanted to be sure that, this kind of event doesn't repeat itself, and they were sure that if they keep the energy down, then it won't happen. And then after that, they went through another shutdown and they fixed all those connections that they were worried about, and then they were able to raise the energy back to the level that the LHC was designed for. Okay, so you can see that as time passed from 2010 to 2011 to 2012, they had an ever increasing number of luminosity. Yes, so just to see, this is in different units. In 2010, they had like 60 inverse picobarn, and then this is, a factor of 1,000 more. So by 2011, they had 27 inverse femtobarn. By 2012, they had close to 30. And the big decisive moment actually came in July of 2012. So that's the amount of data that was actually used for that analysis. And basically, they were able, with that first 2 years of running, able to actually discover that Higgs boson, that particle that I mentioned, has to be there if the mechanism of electroweak symmetry breaking is of the sort that we have been discussing. So here are the main channels in which the Higgs boson is actually being produced. So at the LHC, you are colliding protons with each other. Protons contain both gluons and quarks. So you have to think about collisions of gluons or collisions of quarks with each other. And these are the various processes that would give rise to a Higgs boson in the final state. And then that Higgs boson will decay to possible different ways, and how it decays turns out to be a very sensitive function of the mass of the Higgs boson. So if it's below 100 GeV, yes, then it will mainly decay to B quarks. Yes, as you go between 100 and 200, it really changes very sensitively based on the mass. What the leading decay channel of the Higgs boson is going to be. So the experimentalists had to keep that in mind. And here's the difficulty. Here's the reason why it was so hard to discover the Higgs, both at the LHC and at other experiments. You see, here's the total cross-section for something happening at the LHC when you are colliding protons with each other. You see, in some units, it doesn't quite matter, that cross-section is of the order of 10 to the 7. Yes, and the cross-section for actually producing a Higgs boson, it depends a little bit on the mass of the particle. Yes, let's say 150 GeV. Yes, it is like 12 orders of magnitude smaller than the total cross-section. But that tells you that only 1 in 10 to the 12 of the events is actually interesting for the production of the Higgs boson. And even worse, the decays of the Higgs boson, you can see that actually most of the time, depending on its mass, wants to decay to B quarks. And unfortunately, decays to B quarks is very similar to some of these boring events that are part of this 10 to the 12. So most of those you can actually not even detect. So you have to look for some of those much rarer channels. In fact, it turned out in the end that it was this gamma-gamma channel that was the leading one. Yes, you see, you lose another factor of 100 on top of losing already 10 to the 12. And so you have this gigantic haystack, and you are really looking for a tiny needle in it. And that was what made it really hard. Yes, why it was difficult. But it happened. The experimentalists are really ingenious, and so this was the famous meeting at CERN in 2012, and they actually announced that they finally have discovered the Higgs boson. So actually, Peter Higgs and Francois Angler, two of the people who were responsible for describing the Higgs mechanism, were both present at that meeting, and this is what actually happened. Yes, so it was the discovery in that very, very rare channel. Yes, the one that you may wonder, it's less than 1% branching fraction. Yeah, why should I even bother? Well, that's the one that was experimentally the most accessible for the detection of the Higgs boson. Yes, and what they were able to do is they were able to sort of have this diagram about the invariant mass of the photons in the channel. There are 2 photons observed, and you see that there is a little bit of a peak here at around 125 GeV. And it's what makes it even more complicated is that this is not the only source for generating 2 photons. There are many, many other experiments that are generating 2 photons. Yes, so you see that you have this large background, but then you have this little pump, this little peak on top of it, and that's what is corresponding to the discovery of the Higgs boson. And then later on, they were also discovering it in other channels. So this was the discovery of Atlas plot, and that was at the time of the discovery. Of course, now we have much better plots by after more than 10 years of data. And then Higgs and Angler got the Nobel Prize essentially as quickly as they could in 2013, because in 2012 summer, it was too late to award the Nobel Prize, but in 2013 they got it. Okay, very good. So that's really nice. That's a great success story. We discovered the Higgs boson. Yes. Now what? What are the particle physicists going to do now? Yes. Now, prior to the turning on of the LHC, we were also hoping for many other spectacular discoveries coming from the LHC. One of those is supersymmetry, is one of my favorites, and Professor Roy was also working a lot on this. Another really interesting direction that people were excited about possibly discovering at the LHC was extra dimensions of space, or maybe, the Higgs boson is not actually an elementary scalar, but it's actually a composite particle. In each of these cases, there would be some new particles predicted that would be produced at the LHC as well. Okay, so of course, after the discovery of the Higgs boson, the LHC didn't shut off. Yes, it went on, and it's now focusing on searching for all these other particles, for trying to understand what all these other theories are, and none of these have been observed. So this started to severely constrain, the allowed region for these theories. And so the question that many people are asking, so this is we're relying about all these discoveries. Should I consider the LHC a failure or a success? And I'm not joking, because you probably heard that many people are actually making up stories like the LHC is a great failure because it failed to discover supersymmetry. Okay, so I would like to explain how to really think seriously about when is an experiment or a theory a success or a failure, and what is the correct progression of science, and how should we think about this? Okay, so first the question about was the LHC, not was, because it's still running and it's still going to be running for another decade or more, when is an experiment a success? Okay. Now, the most important experiments usually explore a new frontier of science. Yes, what could be an example? Yes, so for example, when we, sent a spacecraft to the moon, yes, we explored a new frontier, some part of space we never explored, the moon. Yes, same the Mars rovers, they're exploring a region of space that we have never seen before. Medical experiments are exploring new treatments. Yes, space telescope looks further in space than we have ever managed to do before. Yeah, so these are sort of frontier experiments. That's what I call it. Now, in particle physics, most of the new frontier experiments, most but not all, explore new energy ranges that have never been tested before. And so they go to higher energies than what we have ever seen. So the LHC is a prime example for this being an energy frontier experiment. Yes, it explores energies almost 10 times than the previous particle physics experiment that Fermilab did. Okay, so we are in unexplored territories, and the goal of the experiment is to understand what the laws of physics are at those energies. Is it the same? Are those the same laws of physics, or do they have to be changed? Yes. What do I mean by laws of physics have to be changed? Yes. There are clear examples for that. Yes. So, for example, the laws of physics, if you go to macroscopic scales, like this bottle of water, down to atomic scales, the laws of physics in some sense change, in the sense that you go from Newtonian mechanics down to quantum mechanics. Yes, so those things can change. Yes, sometimes when you cross a frontier, yes, the laws of physics change, sometimes they don't. And that's what the main goal of an experiment is to figure out what are the laws of physics at that scale that nobody has previously understood before. Okay, that's the main goal. Yes. And when we have a frontier experiment, by definition, we don't know what the result is. To say that, you know, there should have been supersymmetry and we didn't discover it, so it's a failure. Yes, I mean that's an oxymoron. I mean, if we knew what was there, yes, then it wouldn't be a new discovery. Okay, so I would say that the frontier experiment is a successful experiment if it thoroughly explores that frontier, yes, that it was set out to study. If it discovers anything new, there's even more spectacular success. Yes, of course, you know, that's great, yes, but it's not a must. The must is that you thoroughly explore what is there and what is not there, set the rules of physics at that energy scale, you know, give all the particles that are accessible at that energy and their interactions at that energy. That's what really, you know, an experiment, a good experiment is supposed to do. Okay, so just to put it in a very stark term, yes, imagine the analog of the previous article. This is a fake article. I made it, yes, but just to give a stark contrast, yes. Okay, who would have said, you know, after the moon landing that Apollo fails to find life on moon, the future of space exploration is in doubt? Yes, we could have said this. We spent $25 billion back 1969 dollars, which was 1% of the US GDP over a decade, yes, to send a spacecraft on the moon. Yes, not yet. You know, the laws of physics are the same. There are no aliens there. So this colossal failure puts future space exploration in doubt. Nobody would seriously think that, yes. I mean, it was one of the biggest successes that we could have imagined, yes. We explored this, you know, it's fantastic. And, you know, that was the goal. Yes, and the goal has been achieved. And that's the same about the LHC. Yes. Now let me give you another, you know, striking example. I told you about the previous experiment, the predecessor for the LHC called the LAP experiment. Yes. It didn't discover any new particles. Yes. Yet, if you ask particle experimentalists and theorists too, if they should tell you which experiment do they think was one of the best experiments, you know, they ever remember, surely the lab experiment is going to come up. It's really, you know, it has verified the standard model to an incredible precision. It was really, you know, just worked beautifully. So many precise numbers to calculate and compare. Really, everybody agrees this was one of the best experiments. Yet it didn't discover any new particles. Okay. But it established what the laws of physics are at that scale to an incredible precision. You know, that's now the gold standard. You know, many of the experiments at the LHC, you know, still couldn't, surpass the precision of the lab experiment. So everybody loves it. Okay, so this is really not, you know, I mean, to say that this was a failure would be really weird. Again, you know, you have all these amazingly precise numbers, and they are telling you how physics works. Okay, now what is a real failure? Unfortunately, there have been some, and the most colossal one is called the superconducting super collider. So those of you who were alive or, you know, in physics at the time remember. So this was supposed to be an even bigger version of the LHC, you know, that would have accelerated the protons to 40 TeV instead of 14. So almost 3 times more than the power of the LHC right now. And this was supposed to have started in 2000 or 1999 or something like that. And the quarter of the tunnel was finished, $2 billion were spent, and the entire thing has been canceled. Okay, so that is a real failure, yes, because you sunk in all this money and then, you know, nothing came out of it. And in fact, the US, unfortunately, has struggled ever since the cancellation of the LHC to regain the leadership in high energy physics, at least certainly in the regime of exploring the energy frontier. Okay, so let's try to understand, you know, now what was the situation prior to the LHC. Okay, so we couldn't promise. So those who say, we promised supersymmetry and it wasn't there, it's really not true. We didn't promise. It was one of the possibilities. We could not promise any particular discovery, but what we knew prior to the LHC, and this is what distinguishes now from then, is that we knew that something actually will be discovered at the LHC. And that was a very unique situation. And the reason for that was that we knew that the standard model without a Higgs boson breaks down at energies that the LHC could reach. Okay, so if you take the standard model, the theory that I described to you, and all those precise measurements, if you take out the Higgs boson from it, that theory is actually not consistent when you reach high energies, and high energy can be quantified, and that high energy was actually at the energies of the LHC. Okay, and at the time, before the LHC, there were several ways to cure this problem. So it's not true that, well, I take away a particle. Well, of course, it doesn't make sense because I took it away, so just put it back, yes? Because there were several different things that you could have put back. In fact, one of my favorites was, a theory that, I came up with my collaborators, actually with Christoph also, who was the first Roy lecturer, yes, which we called the Higgsless model at the time. In fact, instead of putting in the Higgs, we could have put in other heavier versions of the W and the Z, and the theory would have been equally successful, except it would not have had a Higgs boson, and it would have a bunch of other particles, and there were concrete predictions for what the LHC would see if there's no Higgs boson, but these other things. Okay, so that was one of the things that the LHC. So it's not true that we knew for sure what the LHC is going to discover. But there were other options at the time. Okay. Now, besides this, there's another sort of new argument that is telling you that something weird is happening at the scales of the LHC. And this is what we call the hierarchy problem. And that hierarchy problem, the way to sort of formally describe it is to say that actually if I have the Higgs boson, the particle that I'm talking about, as an elementary scalar, then if you try to put this in the framework of quantum mechanics, then actually there will be so-called quantum corrections, and those quantum corrections would like to push the mass of the Higgs boson up to very, very high scales. And it's hard to understand why, that didn't happen. Okay, here's a really nice analogy that Riccardo Rattazzi told me about this hierarchy problem, and it's actually pretty precise. Imagine that you have sort of a heat bath of a very large temperature. So there are lots of particles moving in at with very large energies, very large kinetic energies, and you shoot in a particle at energies that are much lower than the temperature of the heat bath itself. And somehow, after a while, you manage to fish out this particle on the other end. Even though it interacted with this heat bath, what you find is that every time you fish it out, the energy of this particle actually remained as low, much lower than the temperature of the heat bath itself. Yes. So if you see something like this, you must wonder, how did that happen? I mean, you know that it's supposed to interact. So the heat bath is supposed to be sort of the analogy of all these quantum corrections, because actually, the vacuum in quantum mechanics is a weird beast, is not nothing. There are very energetic processes happening there, but only for a short period of time due to the uncertainty principle. So this is supposed to be the analogy of the vacuum where all these violent processes are happening. This is supposed to be, sort of, if you think of it, like a little bit like, in, and then there's the interaction here with the heat bath and out. Yes. And if you didn't find that the particle became much more energetic, then something had to prevent this from happening. Yes. So the big question is, what prevented it? Yes. So this is a way to say, what the hierarchy problem of particle physics is. And, surely something must have canceled out these interactions, or the interactions, were not allowed to take place. Yes. So this is why, we were thinking for a long time about supersymmetry, because this was the most prominent solution for this hierarchy problem. And what we thought is that, oh, there must be new particles or new interactions that are such that, you know, these quantum corrections will cancel out. Okay, so in these supersymmetric theories, for every particle, there would be a so-called superpartner. So for the electron, there would be a scalar electron. For the quark, there would be a squark, etc. So for all the particles, there would be a superpartner. So that was one plausible solution. The other really famous plausible solution was the possible presence of extra space-time dimensions. So Lisa Randall, my former advisor, and Raman Sundrum were you know, some of the biggest proponents of this particular solution around 1999. And there, you know, the presence of this extra space-time would be giving rise to taming these quantum corrections that would push the Higgs boson to very high masses. Okay, so those were again really beautiful theories. But then the question is, where is everybody? Again, you know, the LHC, you know, didn't sit idle since 2012. You know, they have worked, you know, with full force on looking for all these other models, and it turns out that, you know, so far they haven't found any hints for supersymmetry or extra dimensions. And in fact, not only did they not find the hint, but they were able to start putting stronger and stronger constraints on these models. So in the simplest versions of supersymmetry, you know, most of the particles, in order for it to really do the job of canceling these additional corrections of the Higgs boson, should be below like 1 TeV or 800 GeV, you see? And now we have bounds that go up to, you know, maybe even twice or 3 times the scale where we thought, you know, the supersymmetric particles actually should show up. Okay, so that's not really good news for these. Okay, so then what's up with these theories? Yes, so okay, so we discussed, okay, the LHC is not a failure. Yes, nobody should even dare saying that. You know, those who say it, you know, don't really understand what they are talking about. But then, okay, but did the theorists lie? Yes. Okay, so then the question is, you know, when is a theory a failure? Yes. Again, you know, we sort of promised all these amazing worlds. The job of the theorists, or at least some of us who work on beyond the standard model physics, is to explore what the possible new particle physics interactions are, and ask, well, by possible I mean that they have not been contradicted by any existing experimental results so far. Yes, and then find avenues to actually give an experimental prediction where you can find this particle or exclude it. Yes, that's what a successful theory does. It gives you a new theory beyond the standard model. It's not excluded yet, but you can find some experimental hints where you can test it, hopefully discover it, but in most cases, you will just exclude it. Yes. So a model getting excluded by experiment is a normal progress of science. So, you know, the fact that my Higgsless theory was excluded, I think that's, you know, I mean, of course, I would have preferred if it was discovered, but it's still great. Experimenters took the effort, they searched for it, you know, these additional particles that, you know, would have been there in our model, it's not there. Okay, fine, that's not how nature works, but it doesn't mean that it was stupid to write down those theories, yes, because it guided the experimentalists to, you know, to look for what the possibilities there are that they should be testing. Okay, so a model would be a failure if it's internally inconsistent or it's already excluded by data, and, you know, people just, you know, didn't analyze all the aspects of it at the time when they predicted it. You know, that's when a theory is a failure. Yes, but the ones that, you know, sort of, you know, give experimentalists, you know, ways to search for new kinds of physics, especially, you know, some of these theories, you know, were really instrumental in sort of getting the experimentalists finding new ways of analyzing the data, because they sort of predicted models which, you know, with the standard analysis methods would not have been found, and, you know, they spurred the experimentalists to look for new ways of testing it. You know, that's actually, you know, even if the theories themselves are not there, this is one of the jobs of the theories. Yes, so, and of course it's natural, you know, you have to predict all the possible models beyond the standard model that you can imagine, and most of them will be wrong, but it doesn't mean that that's a wasted effort. That is the normal progression of science. Okay, so the most interesting theories beyond the standard model are, of course, the ones that would not only be allowed, but would actually make several observable predictions and solve several puzzles at the same time. So supersymmetry was a prime example for that, because it solved the hierarchy problem the way the one that I was talking about before, but it also could have explained dark matter. It predicts the unification of all forces, something that we sort of have some amount of empirical evidence that is actually happening. It predicted many observable particles at the LHC. String theory wouldn't be consistent without supersymmetry. And again, because of these, it used to be the leading and the most favored model for theorists. But it doesn't mean that there was anything wrong with it. Right now there's no evidence for it. So right now there's not that much excitement about supersymmetry anymore. It could still happen at higher energies, but the higher the energy is, the less it is actually going to explain the hierarchy problem. Okay, so now the current situation is somewhat different from that what happened at the LHC, because we don't have a direct hint of where to look for the new physics. Yes? So before the LHC, we knew that at the LHC energies, at least the Higgs boson has to be discovered, and without it, the theory wouldn't be sensible. But it is somewhat unprecedented in the history of science. Yes. Now, of course, does there have to be something beyond the standard model? Of course, again, we can't really guarantee that. But I personally, would be really shocked if, this big program that was started by the Greeks, where we look at shorter and shorter distances, higher and higher energies, and we always used to discover something, would exactly in my lifetime come to an end. Okay, so we have seen several times before when people thought so. Yes, for example, the most famous one was the early 19th, 20th century, when people thought, all we need to do is write these thick books of classical physics, and then we can wash our hands and go home, and that didn't happen. So that's where we are. But we have some hints. The hierarchy problem is still there. Just because supersymmetry wasn't discovered doesn't mean that the hierarchy problem was solved. Yes, it's still there. In fact, it's just getting worse and worse. So we don't really understand what to make of that. Okay, dark matter is something that we know is around us in the universe, and it is calling for some new particles beyond the standard model. In the standard model, it's very hard to understand why all the electric charges of all the particles that we have observed are integer multiples of a basic unit. That is called charge quantization, and there surely has got to be a reason, yes? And, without physics beyond the standard model, we really have no clue about this. Okay, the standard model itself actually does get inconsistent at extremely, extremely high energies. It's called the Landau pole. We will never reach this energy, but an internal inconsistency is there in the standard model. So that is also telling you. And of course, gravity at some point is expected to be quantized too and fit into this picture. So these are all indirect theoretical motivations for thinking that there really has to be something beyond the standard model. The bigger problem is that we don't really have now a direct clue of where this scale should be. And of course, as I said, there is no direct experimental evidence unless you say that the fact that we see dark matter, that's a hint. Okay, so what should we do then? Well, we just discovered the new particle. It's completely unlike any other particle. We should study it to death. That's clearly, that's a must. Yes. So there's the Higgs boson. We have to study the Higgs boson in great detail. Yes. And the LHC has started to do that. And this is, I put up here, the status of the physics of the Higgs boson at the LHC. It agrees with the standard model, but the precision is not very high. There's still about 20%, 10 to 20% uncertainty. So lots of interesting physics can hide in that uncertainty. So we really want some very precise measurement. Particularly interesting ones are the Higgs to gamma gamma, because that only happens at the loop order. So new particles in the loop could have big effects. So here's the future of the LHC. So we are now 2023 here. So this is now what is called the run 3 of the LHC. So this is a run, okay, and it will have a about the same amount of running as was done in the run 2 that gave us the previous set of results. Then there will be another longer shutdown, and then I mentioned that there will be a major upgrade of the LHC, not in terms of energy. The energy will increase just a little bit, but there will be a lot more collisions happening, which is a big challenge to the experimental and the theoretical colleagues, that it will be even harder to fish out what the actual physics is. Okay, now the big question that people need to ask is what comes after the LHC? Well, again, one of the consensus seems to be that, again, we have to study the properties of the Higgs boson in great detail, and probably the best for that would be a circular electron-positron collider, so a bigger version of the LAP experiment that I have talked to you about at CERN. Possible locations could be that people are talking about either CERN or China. And the nice thing about this would be that just like going from lab to the LHC, you could use the same tunnel once you're finished with this circular E plus E minus Higgs, what is now called the Higgs factory, that you could use this for an even more powerful hadron collider, sort of the analog of the LHC, but a factor of 10 higher. Yes, so this could be, at CERN. It could be one possibility. You see, the LHC, this would be a much bigger machine than the LHC itself, or maybe in China. There are several possible sites there. Another option is to do what is called the International Linear Collider. So that would also collide electrons and positrons. The upside of it is that this is ready to be built, and it's interesting, but more limited than the circular machine. The downside is that once you reach 250 GeV, the tunnel has to be extended every time to increase the energy. So it cannot be used for a high energy hadron machine either. Okay, so anyway, that is something that's still in the plans in Japan. It has not been approved, but people are moving forward as if it was approved. I tried to check today if there was any news. I haven't seen anything for 2 years on their website, so I don't know whether that's good news or bad news. Now, recently people were talking about a completely different type of machine, what is called a muon collider. So that would be sort of the analog of an E plus E minus machine, but using, instead of the electron, a muon, a heavier version of the muon. And the big advantages of that is that a muon, because it's heavier, it's easier to accelerate than the electron, it gives less radiation. And because the muon is still elementary, it's also easier initial state than the proton, a much cleaner initial state than the LHC. So you would get all the good volts of the lab and the LHC at the same time. Of course, the hard part is that the muon is not a stable particle, so it's very hard to make a beam that is stable, and it also radiates a lot in form of neutrinos. So that's actually a problem, because if you build an accelerator that radiates 50 kilometers away above the regulatory limit, then maybe such a thing will not be built. So the cost, of course, each of these machines would be of the order of $10 billion in the first phase. So that's a very big sum. Yes, of course, this wouldn't be all spent at once. It would be of the order of 10 years of constructions. The earliest we could see any of these new machines is more than a decade away. And the second phase, like 100 TeV machine, would be, more like 3 decades away. Now, the US wasn't very much on the list of these contenders, as I mentioned. Unfortunately, after the cancellation of the SSC, it's very hard to host a large project in the US. And so I'm not very optimistic that the US will take up leadership in high energy colliders again. But, they are still playing a very important role at the LHC. And course, it doesn't mean the US doesn't do anything interesting. They have a very interesting program in neutrino physics and still leaders in dark matter detection experiments. It's really this high energy part that is missing there. Okay, so in particular, the US just finished the decadal planning process for particle physics in the next decade and in the next 30 years also. And so that's called the SNOMAS process. I was very heavily involved in the theory part of that. And this will be the input for what is called P5, which then decides about the actual projects in the future decade and beyond for the US particle physics. So what should we do? Again, we should, the most important reasons to explore a new frontier is to find out, how does the physics work at that energy scale? Concrete goal would be to explore the properties of the Higgs boson, understand is there a true hierarchy or were we just unlucky at the LHC and there's something right around the corner. Hopefully the accelerator technology will improve. And of course, we always have unexpected spin-offs from, new technology improvements like the World Wide Web was, as everybody knows, was developed at CERN in order to exchange, large amounts of data with each other. It is very expensive. $10 billion is not a cheap experiment, but, just to give it some comparison, I have listed here other projects that are sort of in the similar order of magnitude. Yeah? So this is like, one aircraft carrier, this is Air Force One, here, a football stadium, of course, and I'm not trying to say none of this should be built. I'm just giving you perspective of, this is, the type of investment that these big projects cost nowadays. Yes. And one thing that should be also kept in mind is that, of course, trying to compare it to an individual researcher's lab, the $10 billion is not quite fair, yes, because first of all, the $10 billion is over a decade, and it's for an entire field. It's like several thousand experiments. The LHC experiments, literally have written several thousand papers, and each of those is like a single experiment. And so it's really not quite fair to say that, oh, my experiment in the basement only costs, $2 million. Why should we build a $10 billion machine as if we can do physics for much less? Yes. So that's not the right comparison. Of course, we still have to be sure that, there are good reasons to do it. But again, I just wanted to be sure that, that's put in the right comparison. All right. So let me quickly summarize. Particle physics has the standard model. It's a working framework that describes all the existing experiments in particle physics. The last missing piece from the standard model is the Higgs boson, and that was discovered in 2012. The LHC so far has been a resounding success, and it is, going to go on for at least another decade or more. It will deliver 30 times more data. So the amount of data that we have is just a tiny fraction of the total data that the LHC will be delivering. Beyond the Higgs, so far there's no direct experimental hint for physics beyond the standard model, but we do have some indirect hints from dark matter and from these theoretical considerations like the hierarchy problem or the Landau pole. There are several new colliders that have been planned, mainly outside the US. And, the decisions for these colliders are probably on the 5 to 10 year time scale. And any new machines in the first phase would be at least 15 years away from here, and 30 years for the second phase, like 100 TeV machine. So that's where we are with particle physics. So thank you very much.
Thanks, Csaba. So I guess we will take a few questions. Yes. Let me invite Rick Gupta to handle the question answer session. So there are mics here, and we have volunteers to take them around to you if you have any questions.
So thank you, Csaba, for this very thought-provoking talk. So we have participants here. We have we have participants here and also an audience on Zoom. So we take questions from both groups. So first, let us take some questions from the hall. Please raise your hand. Yes, Gagan.
Yeah, so I greatly appreciate your penultimate slide. Basically, I will do the calculation when I go back home, that what is the sort of per thesis, per paper, the cost for the next collider, but it's greatly appreciated. So on a serious note, like the way you said, you yourself worked on this Higgs-less model, and the fact is it was very, very predictive. Either you have Higgs or you don't have Higgs. And, then when you have the Higgs discovered, then all the Higgs-less model goes into the scrapyard. But
so it's not quite true, because it wasn't immediately like that, because when we discovered the Higgs, we didn't know the coupling of the Higgs. So it could have been that it's sort of a mixture, that, some of the unitary, we call that the unitarization of those processes is happening through an exchange of a Higgs, but it could have been incomplete, and it could have been. So, of course, we were trying to see then, once the Higgs was discovered, is there any room left for, and, more finely, the coupling of the Higgs, that it is standard model like, the less room there is for all these other particles.
Sure.
So that's sort of, the progression.
Correct. But I was talking of the supersymmetry. Of course, we are working on supersymmetry on the experiment side. But my problem with supersymmetry that, although it solves many of the things, the state right now we are in, even if we have the end of high luminosity LSC, of course, we'll do the electrowinner or those kind of searches. There is no prediction where we can say that supersymmetry is yes or no theory, or you can say this is more complex. Right. You're basically moving the ball further and further. So somewhere, can you tell us where I can say that this is no more interesting? Let's give up on that.
Well, let's see, I don't know too many people who write more, papers on, supersymmetric explanations of the hierarchy problem. So it became, it's exactly like you say, you can never really exclude supersymmetry. Yes, you can always push the scale of supersymmetry breaking higher. Yes, but then it solves the hierarchy problem less and less. And that's something that you can quantify. Yes, already at the beginning, before the LHC turned on, there was something called the little hierarchy, and that was something of a percentage type tuning. And now we are in the 0.1 or even fraction of 0.1% type tuning with supersymmetry. So that's the answer. Yes. If you ask a scientist, that's the answer. And then, where do you stop paying attention? Yes. That's sort of more of a sociological question, but essentially the community more or less has stopped paying attention. It doesn't mean there are no interesting applications of supersymmetry. For example, on Thursday, Tuhin mentioned that I will be talking about, using supersymmetry as a lab for strong interaction. So, but in terms of, believing that this is the BSM that solves the hierarchy problem, more or less, it's not everybody, but, it starts sounding less and less likely. So I probably wouldn't put my student on a project like that. I guess that's, unless we have a new idea, it's possible that there's a new idea. And for a while we had new ideas. Okay, how could I have hidden, the gluino at the LHC, R parity violation, for a while you can come up. But then, the experimentalists are ingenious and they search for that too, and they exclude that too. And that at some point, there's no more room to hide. So.
I'm Shashi from CMS experiment. So I just want to, make certain observations or comments. Like, if you look back into the history of all the major discoveries made by the collider experiments, they are all result of the predictions, of a beautiful theoretical framework. We call it as a standard model, but it's a result of theoretical framework. Do you see the similar kind of scenario in future wherein this experiment will continue to search something which is predicted by some framework, rather than having the search mechanism which are not kind of rigidly coupled to the framework on the table.
So right now, again, we have some interesting ideas, but, they are sort of, none of them is a big framework where everything fits together. So I think we really would need the experimental lead right now. That's the situation where we are in, that, the theorists, of course, are really good at, trying to find new directions and also to stimulate the experimentalists for making up different type of experiments or different type of searches. But eventually, it is an experimental science, yes. And we would need an experimental clue. I think that would be that's how I think, the field will progress. Right. We need some discovery. Yeah. And, without new experiments, we are not going to do that. So.
Yeah, thanks. So I just wanted to follow up on that last question. So as I understood, these collider experiments produce vast amounts of data, which you have to filter through to pick up something interesting. And the filter is built on a theoretical framework. You have some idea as to what to look for. So if that framework isn't there, how do you serendipitously find something? How do you find the needle in the haystack?
Right. So it's true that, there's something called a trigger, yes, and there are several layers of triggers that are telling the experimentalists, is this an interesting event or is this an uninteresting event? And because, the amount of data flowing through is so large, it is just physically impossible to record all the data. It's impossible. So like 99.9% of the data is thrown away. Okay, so you're asking, is it possible that we threw away the interesting stuff? And the answer is very unlikely, because those triggers are very, very mild. So they are essentially just looking for, is there anything that could possibly make this? So even if there is a few hard objects, so nothing by hard meaning pretty energetic compared to the energy of the proton. Yes, they already are going to record it. And on top of that, they're taking a sample of even the boring events. So there is a little bit of the boring events that is just randomly picked out and actually recorded, just not the full bandwidth. So, that's what it is. It's nobody could come up with anything better than that. So that's the situation. But again, we are pretty sure that I don't think there's anything that anybody who has come up with an interesting theory that would have been completely thrown out and nothing written on this because of the triggering. But maybe. So that's one of the roles of the theorists, to sort of push the theories and see, could I ever come up with something that would not have been recorded at the LHC, even though it was produced. That is one of the jobs of the theorists, because then if that happens, of course, the experimentalists will say, okay, let's look at your thing and add one more trigger. Yes, they modify the triggers all the time. Yes. Oh. Oh, right. So it depends on what kind of machine it is. But there are certain things that are relatively easy to find. So like the way the Higgs was discovered, even though it took a long time, yes, looking for a bump. That's something that for the experimentalists is a simple and clean experiment. So they will just look for bumps anywhere, and they are doing that now also with the LHC. So they are not just saying, oh, let me look at what supersymmetry predicts and search for that. They just say, I don't care, these theorists often lie to us, I'm just going to look for all possible bumps in this process at any energy. So they do that now. Yes, so that, and that's sort of the most basic experimental work. Yes, so, we don't know what we are exactly looking for, but we know that, what sort of, generic signals of anything new would be. Yes, they would be usually, there's some resonance essentially, and there would be, access over the background, and, they do that all the time, or, sometimes they, they look for abrupt drop-offs. Yes, so those are the kind of things they do. Those searches model independently also. So it's not just, initially, it was somewhat dominated by model-dependent searches, but I think over the last decade, once it became more or less clear that, supersymmetry is probably not the thing that is going to be there, it became more and more sort of just model independent based on, just look for, deviations in this final state, that final state. And then, if you find something, then, the theorists would have to try to come, for example, there was this famous, 750 diphoton anomaly. Yes, for a few months, it looked like, there is an excess in, in the events similar to the one I told you in diphotons. Yes, so that was not, really motivated by any particular theory. People just, whenever they have photons in the final state, they always do that search. And then there seemed to be a bump. Unfortunately, it went away. And then the theorists started, writing papers. I did that too. And I think, and that's also, the thing that, once there is an experimental access, that it is the job of the theorists to try to understand what could it be, what could this be consistent with, and what other things to look for if that access is really true. That is the job of the theorists. So, of course, I'm not saying you should write boring papers, because a good fraction of the papers was boring. Yes, but if you have interesting insights, then you should do that, and that is the job of the theorists.
If we don't know what we look for, and if we don't have a model, isn't this like the prime hunting ground for artificial intelligence?
So people are using that. So there's more and more machine learning. In fact, the collider physics, if you look at HAP-PH articles, a good chunk of them is machine learning based, new methods for collider physics. I'm actually one of the moderators for HAP-PH, and I have this problem that, the field, it's not a problem, it's actually great, but that, so what is still, HAP-PH and what goes into computer science. And, my take is that HAP-PH is what the particle phenomenologists are interested in. So I want to keep those papers in HAP-PH, and but that's happening. So it's not in the far future. And in fact, I think, already soon after the discovery of the top quark, the determination of the top mass, the best determination was based on neural networks. So this is not something that is really new to particle experimentalists. They have been doing this for many decades. Before it was chic to call it machine learning, the particle experimentalists were already there. And
now we have a couple of questions from Zoom, but after that we can come back for maybe a couple more from the room, and I'll especially encourage the students if they have some questions too. But let's go to Zoom and YouTube, where this talk is also being streamed.
Okay, so the first question is by Rajiv Kawai. Rajiv, do you want to ask it yourself?
Hello, can you hear me?
yes.
Okay, great talk. I think, however, that one should be somewhat careful in saying that LHC as an experiment and the theory at that time did not really go with the idea that SUSY will be definitely discovered. In particular, naturalness was used to argue that LHC will discover BSM physics, and there were even no-go theorems that were touted about at that time. Was that, in hindsight, meaning naturalness, a wrong argument? And if today we don't have any better guidance for what a possible BSM scale would be for FCC? Is FCC simply a shot in the dark?
Well, FCC would be the natural next frontier experiment. Yes, I mean, this is how, this is how science is progressing. Yes, you explore one range of energies. Yes, and then once you thoroughly explore it, it's of course very important that you thoroughly explore it. Yes, then you move on to the next. Of course you may say, let's just stop exploring. Yes, that's the other option. Yes. Okay, I mean, if you're not interested, I'm not saying you specifically, but I mean, if people are not interested in what is there anything possibly there? Yes, then no. But I think the reason to explore that range, the highest motivation is to just find out, is there anything there or not? Yes, I think the hierarchy problem is definitely a problem. Yes, we don't understand it. Again, we don't know whether it's just unlucky that the LHC just happened to be at a just slightly not enough energy, but it doesn't quite look like that, at least to me, because we don't even see sort of hints and tails, and but then something's gotta explain. I mean, it's not like the hierarchy problem is a made-up thing. Yes, I mean it. On the other hand, the hierarchy problem is not really a problem in the sense of, the consistency of the theory. Yes, the consistency of the theory has no problem if it's fine-tuned. It's an issue of tuning. Yes, it's the kind of tuning that we have never seen before, in physics. If new particles are not the solution, then something else is probably. So, people are, so some of the theorists, like, Rick himself, is thinking about, new approaches to the hierarchy problem. Yes, where we say, okay, so if it's not new particles, yes, then maybe there's some other kind of explanation for, how the Higgs has achieved that mass. So you may have heard about things like the relaxion. There, really, in those theories, what happens is that there's no specific value of the Higgs mass that is stable, but something very special that happens when the electroweak symmetry breaking is actually happening, and that is giving rise to the new physics that is choosing that scale. So if you are asking, should we explore other possible approaches to the hierarchy problem? Absolutely, and we are doing that. I mean, though many of those, that's actually one of the main themes nowadays in beyond the standard model physics. But of course, it's still try to keep in mind that there should be some experimental predictions. So those, I think, are very worthwhile endeavors, and we should do all of these, I would say.
So the next question is by Tejinder Singh. Tejinder, would you like to ask yourself?
Maybe you can read it if you have it.
Yeah, I'll just read it out since he isn't able to unmute. Okay, so he asked that the standard model has 26 pre-parameters, which seem to take arbitrary values. And since there is no compelling reason to believe that discoveries at higher energies will bring this number down, how are then we to understand the origin of these values? For example, the mass ratios.
Right, so that would be, of course, that's another really good motivation. But so the kind of question is, why is the top quark, 10 to the 5 times heavier than the electron? Yes, I would really love to know that. And of course, that is a direction that particle theorists are trying to explore. So they are trying to make so-called theories of flavor. Now, the problem is that, whenever you introduce, sort of new flavor models, usually it's very, very tightly constrained game. And the scale of new physics, of generic new physics that introduces generic new flavor structures, is much higher than the scale of the LHC. It's like 10 to the 5 TeV-ish. Okay, then of course you can have, more symmetries, and so it's an interesting problem. Yes,
Can I respond to that, please? I was the one who asked that question. Yeah, the point is we theorists believe that we understand the theory part at the current energies very well.
Right.
And I think that's questionable. Gravity is to be ignored, totally agreed. What are we left with? Quantum field theory and special relativity. Now, special relativity gives us a 4-dimensional space-time manifold labeled by 4 real numbers. But this is a classical construct. It can be shown that I can talk of a point structure of space-time as in special relativity only when the universe is dominated by classical bodies. No gravity, but even the manifold requires classical objects. So it turns out that in a true version of quantum field theory, even at LHC energies, you should be able to describe the standard model without using the classical space-time manifold and instead use non-commuting numbers. When you do that, it can actually be shown that we understand things like mass ratios or values of coupling constants like the fine structure constant. So the issue is not that we need to go to higher energies. There's something amiss in our understanding of quantum theory and space-time already at low energies. And I would urge, particle physicists to look in that direction. And maybe it would be good to know your opinion on this.
Well, so about non-commutative theories, so usually the ones I have seen, they have very strong constraints, very strong experimental constraints. So I didn't find those particularly exciting, the ones I saw, but I'm not sure I saw yours. So I think, people should, if they have some new ideas of finding the, origin of flavor, that's very exciting. So
perhaps we can have one more question from the audience, from the hall. Anything from the students, maybe something? Okay, so if not, we'll thank Csaba again for this very nice talk, and let's applaud him again, and then.
So, yeah, so thanks Csaba again. I would also like to express my thanks to Dr. Monica Roy. I see Kalyani is also here, to Kalyani Roy, to TIFR director for allowing us the use of everything needed to do this. Our public relations office for organizing everything, including advertising this talk elsewhere. Auditorium staff who has made it seamless for us to organize this. The photography section. And the canteen, which as we speak is ready outside for some small refreshments for us. And of course, you, the audience, for being here for this 4th public lecture for DP Roy Memorial. Professor Csaba Csaki he's going to be here visiting us for about a month. So those who are interested can come and contact him, talk to him, maybe start collaborations with him. He is going to give 2 more talks this week, one tomorrow at 4 o'clock as a DTP colloquium, and one on Thursday at 2:30 as a free webinar seminar. So please feel free to come to that also. So with that, let me declare the end to this public lecture event, and let's go out, maybe have some tea. Thanks.